Alright students, we're going to begin what I hope is the last video of this chapter. This particular one is going to be Dalton's Law of Partial Pressures, which is fairly easy section of the chapter, and mole fractions, which can be, we're not going to go into too much detail using it, and then using those partial pressures to solve some problems. Now don't let this sigma throw you. It simply means the sum, and you've seen that before, the sum. And so the total pressure, that's what the P stands for, the total pressure is equal to the sum of the individual partial pressures. And so the simply means that Dalton said that the total pressure on a mixture of gases, just like our air is a mixture of gases, we've got oxygen, we've got nitrogen, carbon dioxide, water vapor, we've got lots of different gases that are mixed in our atmosphere. And so if we want to know the total pressure, we can take the individual pressures of each gas and add them up and get our total pressure. So that's what it says. So you can use each the ideal gas law to find the partial pressure of each gas and then add them all up. That's what that's saying. Okay, so here you have this 1 liter vessel, and it's got some nitrogen gas, it's got hydrogen gas, both of these two gases, and they're both at 25.5 degrees Celsius. So determine the partial pressure of each gas in the vessel. And so you're going to first convert your Celsius to Kelvin by adding your 273.15. That's where they get this. This is in your textbook, by the way. Sample problem 10.12. So to find the partial pressure, what you're going to do, let me get a pen here. What you're going to do, since you have 1 liter, that's easy enough. Your volume is 1.00 liter. Your temperature, we just found it, is equal to the 298.65, and both of these gases are in the same vessel, they're in the same container, so they both have the same volume, they both have the same temperature. What they don't have is the same pressure, and that's because they weigh different. And so that should make sense to you that a heavier gas is going to, remember what causes pressure in a gas. Pressure is caused in a gas when it hits the walls of the container or it hits other gas particles. And a heavier gas particle is going to hit with more force than a lighter gas particle if they are traveling at the same speed. How do you know they're traveling at the same speed? Because they're traveling at the same temperature. And temperature measures speed. You must get that in your head. Temperature measures the kinetic energy, or how fast the gas particles are moving. That is crucial to your understanding of the gas laws. Pressure is how hard they're hitting in a contained vessel, and temperature is how fast they're moving. It's a measure of their kinetic energy. In other words, it's a measure of their speed. Get those two things in your head and you're good with these. Alright, so let's then, if we're talking about the nitrogen, let's find the pressure of the nitrogen gas. Okay, so we know that PV equals nRT, and if we want to find this in using the 0.08206, then that's the R that we're going to use. Okay, so we could use that one, that value for R. This would be your setup, the 0.08206 one to find your nitrogen gas. There is your setup. You're going to use your pressure for your nitrogen is simply going to be the moles times your value for R, the 0.08206, and then times the temperature. And you're going to divide it then by your volume. You're going to get that number of atmospheres, and you're going to do the exact same thing for your hydrogen. You got your number of moles of hydrogen times your value for R times your temperature divided by your volume to get that pressure. And then to find the total pressure, you just add those two together. So it's not too bad. That's Dalton's Law of Partial Pressures. All right. Then let's talk about mole fraction. First of all, mole fraction is a comparison, okay? So it's going to always be less than 1, and it is a fraction. So when you add them up, it's always going to add to be 1. So it's an idea, or it's a value, it's a ratio. Does not have units because you're comparing. So what you're doing is you're getting an idea of which has the most pressure, which is going to contribute the most pressure in a mixture of gases. That's what you're basically doing. Okay, notice what you can do here. The mole fraction times the total number of moles is going to equal that mole fraction, okay? And then if you know the total pressure, then you can find the partial pressure if you know the mole fraction. That's pretty straightforward. Let's see how you calculate this. Again, this is from a problem that's in your text. Sample problem 10.13. If you want to know the mole fraction for a gas that's in a 10-liter cylinder at room temperature, and it's got 6.22 moles of nitrogen, and the total pressure, and you got your total temperature right there. Notice what you're going to do first. If you know your pressure, you're going to use your PV equals nRT, your ideal gas law, to find your number of moles. But you say, oh, but we know how many moles. No, you know how many moles of nitrogen. You don't know the total moles in the container. Okay, so you want to find your mole total number of moles. So you're going to find the moles in the container and subtract it off, and that's going to give you your moles of NO. So you're going to use your PV equals nRT, solve it for N. Please be extremely careful. Again, when you do this division right here, please be super careful that you put this divided by this, or else put another big giant parenthesis around everything in the denominator, or you're going to get an incorrect answer when you do that. Okay, so that's going to equal 6.29 moles, and then you're going to take that 6.029 and you're going to subtract off the moles of nitrogen that it gave you in the problem, and you're only going to get 0.007 moles of nitrogen monoxide, which is what it gave you, what you're looking for, okay? And then how are you going to find the mole fraction? You take that 0.007 moles of nitrogen monoxide, and then you divide that by your total number of moles in the problem that you got from your PV equals nRT. And so 0.007 divided by your total is 0.001. That's your mole fraction. Okay? Now, why do you care about mole fraction? What can you use mole fraction for? It compares the components in a gas mixture so that you can eventually get your partial pressures. That's what your goal is to get partial pressures so that you can solve problems with it, as in this next one. Okay? Now we've already solved a couple of gas law problems, and you've seen what they can be used for. So let's go about solving some more, using them to solve some problems. Here's a pretty practical problem where they're actually producing some oxygen. This is a very standard way to produce oxygen gas. They've got a vessel in which to catch the oxygen gas they're produced. They've got a water bath and some rubber tubing. And then notice the rubber tubing is being put into the water bath and then up into the vessel, so that, and you can see here the bubbles of oxygen as it's being bubbled up. And then as the oxygen gas is produced, the water level in the cylinder comes down, and that's because pure oxygen is bubbling up into that and pushing it out. Alright, that's what's happening in this case. Let's look here. Calcium metal, this is in your textbook. This is on the bottom of page 441 in your textbook, where it says calcium metal reacts with water to produce hydrogen gas. Determine the mass of hydrogen produced at 25 degrees Celsius and 0.967 atmospheres when 525 mils of the gas is collected over water. So the 525 mils is your volume, that you'll need to change that into liters. You're looking for your mass, so you're looking for your grams. In the long run, that's exactly what you're going to be looking for. You know your pressure. Look at everything that you know, okay? Look at everything you know. Now, they have chosen in this case to switch their pressure into atmospheres. Now, let's think for a minute why this author would choose to do this. This author chose to switch her units into atmospheres because R, the value for R that apparently she likes the best is the 0.082061. So that's what she's using. Okay? And that's what our atmospheres up there is given in. We want them to be in the same units. So you're going to switch. You have to switch one or the other. So they chose to use the one with atmospheres in it. Alright? So let's see what we do with this now. You have to consider the water vapor, because water vapor is mixed in here too, so you have to consider it as well. And if you'll look on page 441, it talks about it says in the middle of the page, it says because you've got the volume that's in this cylinder, it contains both oxygen that's made by the reaction and by water. It's got some water vapor mixed in there with it. You have pressure that's inside that cylinder that comes from both places. It's made by this reaction, but you've also got water in there. See that H2O? So you got that water vapor from that too. You have to consider that as part of your pressure, so it's adding to the mix. And you have a table that's on page 441 in there, and it shows you vapor pressure of water at these different temperatures. And if you'll look in here in this table, table 10.5 on page 441, it shows you that at 25 degrees Celsius, the vapor pressure is 23.8 torr. That is where that number came from, and then they switched it into ATMs. And they switched it into ATMs because the 0.967 was in ATMs, and you have to have them in common units. Alright? So you're good there? And also notice that our we're looking for the molar mass. We're looking for the mass of hydrogen gas, and so you also need to know the molar mass of hydrogen gas from the periodic table. 1 mole of hydrogen is 2.02 grams. We worked on that long chapters ago from stoichiometry. Alright, so our let's look how we set this up. I would have set this up just a little bit different myself. I'm going to show you exactly what I would have done. I would have done like this. I would have said my total pressure, I know, is equal to the pressure from the hydrogen plus the pressure from my water. I know this. I'm sorry, I know this right here. Okay, and I also know this. I do not know this. That's what I'm looking for. So how can I find my hydrogen? Well, now I'm going to get that hydrogen by itself. So the pressure of the hydrogen is going to be equal then to that 0.967 atms minus the pressure of the water vapor, 0.0313 atmospheres. That's where she gets the 0.936 atms. That's where that comes from, right here. Okay? Then you're going to use your trusty handy dandy. PV is equal to nRT. And we are looking here for P. No, I'm so sorry. We are looking for N. That's what we're trying to solve for, is our N. How are you going to get that N by itself? We're going to divide by RT. We're going to divide by RT. So those go. So N is equal to PV divided by RT. Well, there's our T right there. There's our R. There's our our P, and there's our V. So we know everything. So you're going to say your pressure times your volume. Don't forget to change that milliliters to liters. Divide by 1,000, change it to liters. Get those two. And there's your R, the 0.08206, and there's your temperature, 298.15. And once you do all that, you get your grams. And you're still not finished. Why aren't you still finished? Because this is grams, and it asks you to go from grams to moles. How are you going to go from grams to moles? You're going to go from grams to moles using the molar mass. Okay? Or I'm sorry, I need to just start over. This gives you moles, and you're asked to find grams. So how are you going to go from moles to grams? You're going to still use the molar mass. You've got to use the molar mass to finally give you the grams. Okay? The only other thing that we lack for this particular chapter is diffusion and effusion, and what that has to do with the kinetic molecular theory. And I'm not going to go into a huge amount of detail here, but basically what you need to know is smaller gases, and I've already explained this to you. The smaller gases, not only do they have less pressure when they hit, but they can also go faster. They can go significantly faster because they're lighter, and that makes sense. A gas is made of particles that are separated far apart. We already talked about that. They're very far apart. And a gas is usually mostly empty space. Gas molecules, they're moving very fast, and they're in constant random motion. And those particles, they follow the law of inertia. They're going to travel in mostly straight lines, and they're going to hit the walls of the container, and they're going to run into each other. And they're going to have perfectly elastic collisions. That means if they bump into something, they're going to maybe transfer some of their energy to that other particle, but no energy is lost. Okay, that it doesn't, overall the energy is not lost to friction or to anything else. The total energy is going to, if I lose a little bit of energy, then the particle that I hit gains that energy. Okay, and then those gas particles are not going to be attracted to each other. So there's no attractive or repulsive forces between the particles. That's what the kinetic molecular theory of gases says. Now, what does that have to do anything? I've already told you most of this. It pretty much says that, please keep in mind, that temperature measures how fast the gas particles are going, okay? And in science words, that says that the average kinetic energy, notice the E there, K sub K, is directly proportional to the absolute temperature. That is the Kelvin temperature. And so you can use the physics definition of that also. The kinetic energy there is equal to half the mass times the velocity squared. That is the kinetic energy formula right there from physics. Okay, we will not do this mean square speed. We could do it, but you can simply see that since the mass is involved, that certainly lighter molecules are going to be able to travel faster. Okay, and we also know that you can compress gases. We also talked about Boyle's law here. Okay, if you understand what causes pressure in a gas, the particles hitting each other in the walls of the container, it does make sense. Boyle's law makes sense. If you understand that pressure in a gas is caused when those particles hit each other, collide with each other in the walls of the container, if you give them less space to move around, they will hit each other more often. So pressure is going to increase. So it certainly makes sense. Decreasing the volume by half is going to double the pressure. Certainly makes sense, yeah? And so Charles' law, we talked about this as well. If you heat, increase their energy, make them move faster, you better give them more room to move around. Okay? Again, already talked about all of these things. Okay? And here we're talking about speed. How much does it speed up? And we could derive it using your PV equals MRT, and we could talk about the number of moles and all of those kinds of things. But I'm not going to ask you to learn this, okay? What I will ask you to know is this last one right here, that you can compare two gases and decide which one of them is going to travel faster. That italicized capital M right there like that means molar mass. So if you have the square root of the two molar masses, you can compare two of them and you can calculate which one is going to be faster. And certainly the one with the smaller molar mass is going to be faster, but you can find out exactly how much faster. Now what I care about is that you know, hey, this smaller one is going to travel faster, but you can actually calculate how much faster. Okay? And you can see there exactly how much faster. The speed of the first one is equal to, over the speed of the second one, is equal to the square root of the molar mass of the second one over the molar mass of the first one. Okay? So you can see this in the sample problem 16, that how much faster helium atom moves on average than a carbon dioxide molecule at the same temp. And it shows you their molar masses right there. So you're simply going to take 44.01 divided by 4, that's 11, and you're going to take the square root of 11. So that's what you're going to do. The square root of 44 over the square root of 4 is 11. The square root of 11 is somewhere around 3.3. So on average, it's going to be 3.3 times faster. Helium is going to be 3.3 times faster than carbon dioxide. That's all you do. Okay? And then you do need to know what is diffusion and effusion. You do need to know the difference between the two. Diffusion is, I bring a bottle of perfume and I accidentally spill it in a room. Okay? And it's random, and they collide with each other. The particles collide with each other, and they mix together. That's diffusion. All right, diffusion. So they're mixing together until everything's equalized, and they will always mix until all the particles are randomly mixed together. Effusion is a gas that has more particles escaping into where there's fewer particles exist, or a vacuum. Okay, that is effusion. There's a little tiny hole in a balloon or whatever, and the gas leaks out or seeps out of that hole. That is effusion. Into where there's a vacuum. That's effusion. That's the difference between the two. Okay, diffusion, you open that perfume or whatever, and the gases, there's gases in both places, and they mix together until it's random. Effusion, there's a vacuum here, there's not a vacuum in this other place, and it escapes through some hole, and it gets in there. Effusion. Okay. And then Graham's law states that the rate of diffusion or effusion is going to be proportional to the square root of the molar mass. So the heavier the gas is, the slower that's going to occur, proportionally. And then the only other thing that I would ask you to know from this chapter is that everything that we've talked about is if a gas behaves every single rule all the time. Now, Boyle's law and Charles' law says that a gas, if you increase the pressure, the volume is going to decrease. Charles' law says if you increase the temperature, the volume is also going to increase, ideally. Now, an ideal child will always obey every single rule as well. Every single thing that you ask it to do, that child will obey. Never disobey. There is no such thing as an ideal gas, just like there is no such thing as an ideal child. Okay? But when will a gas behave most ideally? That's what you need to know. Okay? So what I want you to know is when gases will behave most ideally. And right here, let me see if I can find that slide, just one second. Gases are going to behave most ideally at very high temperatures and very low pressures. Okay? And it says right here, when molecules move more slowly, they have a lower kinetic energies, and then the forces become more significant between them, so they become more attractive forces, so that's going to cause them to behave less ideally. Okay? Because at low temperatures, they're going to be moving more slowly. All right? And then at high pressures, so you want to make sure that you have high temperatures and low pressures. High temps, low pressure. High temp, low pressure. That is when a gas behaves most ideally. I will expect you to know that for your test. Okay? High temperature, low pressure. That's when a gas behaves most ideally. All right, I hope you're ready for this test. And then we just have one more tiny little chapter. We will not cover the entire chapter. We're just going to cover sections of it. And I like it too. So I hope you enjoy.